Thank you so much. Thank you to the organizers for inviting me to speak here. I'm really excited. So I'm going to be, like Maria said, inviting you to equivariant Ehrhart theory. This is a topic that I've worked a great deal on in the past few years. And so now, as it says on my slide, I'm actually going to be leaving academia in the fall and starting as a developer at ComSol, which is a company that makes multiphysics software. So I'll be still doing polytopes, actually. I'll be like developing their geometric algorithms. So I'm really excited for that. But that means that, I probably won't be working on equivariant Ehrhart theory after like a few months from now. So that's why I'm really excited to talk about it here and like try to bring more people and get more people excited about this. And also I want to shout out during my talk, like some people who are, currently still in academia who are like actively working on these problems. So my goal with this talk is to sort of give an overview of like the setup of equivariant Ehrhart theory. I'll describe an example of how one would compute this. And then there's like a number of different techniques that we can use to compute equivariant Ehrhart theory. So I'll basically just describe one of them because I don't have time in this talk to talk about all of them. But at the end, I'll sort of give an overview, like a list of the different things that have been done and by whom, and I'll mention some further questions. So that's the outline of my talk. Great. Okay, so I'll be talking about two projects that I've worked on. One is with Federico Ardila and Andrés Vindas-Meléndez, and then the second is with Sophia, Elia, and Donghyun Kim. So the previous one was published in 2020, and this one's from 2022. So to start, we'll be working in a subvector space. I believe for pretty much all the examples I'm going to talk about, the vector space is R to the n quotiented by the all ones vector. And then we have a polytope in our vector space that can be defined in one of these two equivalent ways. So either it's a bounded intersection of finitely many closed affine half spaces, as in the left-hand picture here, or a convex hull of finitely many points, so the smallest convex set containing some finite set of points, as seen in the right picture. And then in particular, we'll need a simplex, which is a polytope with the minimal possible number of vertices. So in 2 dimensions, this will be a triangle, in 3 dimensions, a tetrahedron, and so on. So in our setup, our polytope lives in some vector space, for example, R to the n, and we also have some lattice living in this vector space, which you can think of as z to the n, the integers. And then we define this function called the lattice point enumerator, which takes in a positive integer t, and it simply outputs the number of integer points in the dilate TP. So TP is what you get when you take your polytope and you multiply every point by the positive integer t, so you're just dilating it, and then we're counting the number of integer points in that dilation. So a priori, this is just a sequence of numbers indexed by positive integers, but remarkably, Ehrhart's theorem tells us that this agrees with a polynomial of degree d, where d is the dimension of the polytope. So if you look at the example at the bottom of the slide, you'll see that if p is our unit square, then we have 2p and 3p, and we can see that the pattern of the number of integer points is, well, in p we have 4, in 2p we have 9, in 3p we have 16, and the lattice point enumerator ends up being t plus 1 squared. And we call this the Ehrhart polynomial. We know some extra information about the Ehrhart polynomial, so we know the constant term always has to be 1. The coefficient of t to the d has to be the volume of the polytope, and the coefficient of t to the d minus 1 we also know, and it's related to the number of lattice points on the boundary of the polytope. Okay, so then as combinatorialists, we like to often take our sequences and use generating functions to think about them instead of just thinking of a sequence of numbers. So we do that here. We construct the generating function where the coefficient of z to the t is the lattice point enumerator, the number of integer points in the dilate TP. And this is called the Ehrhart series, and it always has this nice rational form where the denominator is 1 minus z to the dimension of the polytope plus 1. And the numerator is this polynomial we call the h star polynomial. So this is a polynomial that always has degree at most d and non-negative coefficients. And we can also think of this Ehrhart series by taking our polytope and raising it to height 1 in a space of dimension 1 higher, as I've done in this picture on my slide. And then we take the cone over the polytope. And if we slice that cone at the positive integer heights, then we get the different dilates of the polytope. And so we can think of this Ehrhart series as the Hilbert series of the graded algebra generated by these lattice points in this cone. So for our example with the unit square, we get that the Ehrhart series is, as I've written here on the slide, so the h star polynomial is 1 plus z in this case. If you're bored, you can check that using your Taylor series expansions. Okay, so so what I've told you so far is the setup of classical Ehrhart theory. And lots of people study classical Ehrhart theory. They study the properties of these Ehrhart polynomials, h star polynomials, and also try to characterize them and look at how the different properties of the polytope might show up in these polynomials. And now what I want to do is take it like one more level of generalization, I guess. Well, I guess you could call it generalization. I don't know. Anyway, adding one more layer, I guess. So I'm going to introduce equivariant Ehrhart theory, and this was originally introduced by Stapledon in 2011. And so now we have our lattice polytope P, and we have some group G of linear symmetries of P. And so along with this, we get a representation rho and a family of representations chi sub TP. So here rho is going to be, you can think of rho as the function where you plug in an element of your group of symmetries and it outputs the matrix that tells you how that group element acts on the vector space. And then we have this family of permutation characters, chi sub TP, one for each positive integer t. And this is like the analog of the Ehrhart polynomial, the equivariant analog. So this is a permutation character given by the action of the group on the lattice points in that dilation TP. So you can think of this as a function that takes in a group element and it outputs the number of lattice points in TP that are fixed by the action of that group element. And we'll see this in example in a slide or two. But I want to finish saying the whole setup first, and then we'll walk through an example. So just like in classical Ehrhart theory, we can construct the equivariant Ehrhart series. So instead of putting the lattice point enumerator as the coefficients, we put these characters, these chi sub TP. So we have a series whose coefficients are characters of the group. But if we plug in a group element, then what we're going to get is the Ehrhart series of the subpolytope of P that's fixed by the action of that group element. So we'll see this in an example in a second. And then Stapledon showed that this equivariant Ehrhart series also has this somewhat nice predictable form where the denominator is it's given as here. So it's 1 minus z times the determinant of the identity matrix minus rho times z. And the numerator is this analog of the h star polynomial that we call the h star series. And now it's not necessarily a polynomial, it could be a series, we'll see this. So now in equivariant Ehrhart theory, we want to study this h star series and like think about when it does have some nice properties. So in particular, so this is a series whose coefficients are integer linear combinations of characters of G. And so some questions we might ask is, when is this series actually a polynomial? So it's finite and it doesn't go on to infinity. Or also, when is it effective? Meaning that all of the coefficients are characters of the group, which means they're positive integer linear combinations of characters of G, not just any integer combinations. Okay, that was a lot of setup, but then we'll walk through an example now. Okay, so I want to do an example of this hexagon, the permutahedron. So the vertices are the different ways of ordering the coordinates 1, 2, 3. And I'm going to take the group action. So the group is going to be S3, the symmetric group, and it's just going to act by permuting coordinates of points. So the representation that's underlying this action is the standard representation of S3. And so what we want to do is we want to look at each element of S3, and we want to look at the subpolytope of the hexagon that's fixed by that element. So I've already helpfully put here, if the group element is the identity, then the whole thing is fixed, and so the fixed polytope is the whole hexagon. So next, we can look at the transpositions. So for example, if we take the transposition 1, 2, this is swapping the first and second coordinates of points, or in other words, it's reflection across the hyperplane x1 equals x2. So if we do that, we can see that hyperplane is this like horizontal line through our hexagon, and the fixed polytope is going to be the intersection of the hexagon with that axis of reflection. And so here we get this rational line segment, 3 halves, 3 halves, 3 connected to 5 halves, 5 halves, 1. And you can see this is a rational polytope. So it's no longer integer coordinates, but we still have like a version of Ehrhart theory that works here. And it does still contain a lattice point, this point in the middle. So for each of these transpositions, we get a rational line segment like this. And then lastly, we need to look at the 3 cycles. So this is sort of like cyclically rotating coordinates. And when we do that, only this point in the middle, 2, 2, 2, is fixed by that action. So the fixed polytope is just that point. Okay, so these are the fixed polytopes that we get. And then what we'll do is basically we'll look at the Ehrhart series of each of these fixed polytopes, and then we'll like sort of go backwards, I guess, to the characters of S3 and figure out how to use linear combinations of the characters of S3 to get something that evaluates to the Ehrhart series of each of these fixed polytopes. So I have this helpful table here. So in this case, the denominator, this thing with like determinant of identity minus rho times z. In this case, it's the product of 1 minus z to the cycle lengths of sigma. So we have to sort of break this down based on cycle type. So if we have the identity, so the cycle type 1, 1, 1, then we're just doing in the second column, this is the Ehrhart polynomial of the fixed polytope. So we have here the Ehrhart polynomial of the hexagon. When we do the Ehrhart series of the hexagon, we get this one here. So you see the denominator is 1 minus z cubed, just like it should be according to this denominator we want. And then we take the numerator, and that's what we should get if we take this H star series and evaluate it at the identity. So we should get 1 plus 4z plus c squared. So we can do that for each of these other cycle types. So if we have a transposition, we get this rational line segment. And so then the Ehrhart, well, the lattice point enumerator is now no longer quite a polynomial, but we get this periodic function that just depends on whether you're doing an even or odd dilation. So this is the function that tells you how many lattice points are in the dilation of that rational line segment. And then if we, construct the generating function of that, we get this thing in the third column, which you can see again has the correct denominator that we need, product of 1 minus c to the cycle lengths. And so the numerator is what the H star series should evaluate to when you evaluate it at a transposition. And finally, for the bottom row, we have 3 cycles, and that's just going to be the Ehrhart polynomial series of this point. That was what you get when you take the fixed polytope of the 3-cycle. So now finally, to put it all together, I'm going to look at the last column here, and then I'm going to think about the characters of the symmetric group S3 and think about how I can combine them together so that the constant term evaluates to 1 for all of the elements of the group. The linear term evaluates to 4 for the identity, 0 for transposition, and 1 for a 3-cycle. And the top term also has to be 1 for everything. So that's how we get this expression down here for the H star series of the hexagon with this particular group action. Okay, so this is pretty nice. The H star series is a polynomial because it only has, we don't have like an infinite number of terms of higher and higher degree. And it's also effective because you see that, so each of these, you'll have to believe me on this, but each of these like chi's is a irreducible representation of the symmetric group. And so when we're taking positive combinations of them, we're staying at an effective representation. So this is like sort of a nice equivariant Ehrhart, equivariant H star series. If we go 1 dimension higher and we take the 3-dimensional permutahedron, we can do the same thing. So now I don't have a picture to show you, but we look at each cycle type of S4. We construct the Ehrhart or the lattice point enumerator of the fixed polytope for a group element with that cycle type. We can construct the Ehrhart series for that fixed polytope, and then make sure the numerator is what we need it to be, and then make sure the denominator is what we need it to be, the product of 1 minus c to the cycle lengths, and then take out the numerator, and that gives us this last column. So here, something a little bit ugly happens, which is if we are working with a transposition acting on, so basically a reflection across a hyperplane, like xi equals xj, acting on the 3-dimensional permutahedron. If we look at the fixed polytope, when we take the Ehrhart series, it's gonna have extra terms in the denominator that are not accounted for by this product of 1 minus c to the cycle lengths. We have this 1 plus z squared. So that has to be considered to be like part of the numerator, part of the H star series. And that's why we get an infinite series for that particular group element. And so if we then again like try to express this in terms of the characters of S4, we end up with this like much uglier expression down here where you can see now, because of the case with transpositions, it's not polynomial, and it's also not effective because we have some negative signs in front of some of the irreducible representations. So okay, oh yeah, and maybe I'll make a comment that this equivariant Ehrhart theory of the symmetric group acting on the permutahedron was done by Federico Ardila and Andrés Vindas-Meléndez and myself. And we used the fact that the permutahedron is a zonotope in order to do this, which is one technique in equivariant Ehrhart theory that I'm not going to be able to really get into in the talk, but that's like sort of one direction you could go down, is like exploiting zonotope structure. So Stapledon in his original paper conjectured that polynomiality and effectiveness are equivalent conditions for the H star series. And he showed that effectiveness implies polynomiality, so it's just the other direction that's conjectured. And so one big question in this field is, does polynomiality imply effectiveness? He also had this third condition that he conjectured was equivalent, but that was actually shown to not be equivalent to the other two conditions. And you can see, so that was done by Santos and Stapledon, but they didn't publish it. And so they allowed Sophia and Donghyun and I to write up the proof in our paper. So if you want to see the proof, you can look there. Also, when the polytope P that you're working with is allowed to be rational, then the conjecture actually is not true. So polynomiality and effectiveness are not equivalent. And this was shown really recently by Clark, Coble, and Higashitani. So when it comes to the permutahedron, so Federico and Andrés and I showed that the H star series was a polynomial if and only if basically you're the hexagon or like the line segment or like the point, so the very low dimensional Permutahedra. And for the 3-dimensional one and above, the H star series is not a polynomial. And so as a corollary, we get that Stapledon's conjecture holds for all Permutahedra under the action of the symmetric group. But in some sense, this is like not, it almost feels, well, so although you would think that the symmetric group would be the natural choice to act on the Permutahedron, in the sense of equivariant Ehrhart theory, it's like too big of a group to have a nice equivariant Ehrhart series. And that was very surprising because you kind of want it to like be nice, right? So one question that we have is what's the largest subgroup of Sn where you do get a polynomial and effective H star series? So Sophia and Donghyun and I showed that you always have polynomiality when you restrict to the cyclic group. And then we showed effectiveness, but only when n was prime. And so the effectiveness for non-prime n is open. So that's sort of one thing that we were thinking about, is like subgroups acting on the Permutahedron. Okay, so that's kind of like an overview of some of these questions and an example. I want to get into one technique that Sophia and Donghyun and I worked with. And this has to do with invariant triangulations. So this is where we need simplices. So in classical Ehrhart theory, we have a way to triangulate a polytope into lattice simplices and sort of build up its Ehrhart polynomial by counting, or its H star polynomial by counting the lattice points in all of these simplices. So we wanted to see if we could generalize that to the equivariant setting. And so if we have a d-dimensional simplex with these d+1 vertices, we can construct the fundamental parallelepiped over P, the simplex, which has this formula here, so it's half open. And in particular, it doesn't include actually the vertices of the simplex. And then if you want to look at the H star polynomial of a simplex, well, the coefficient of z to the I is just the number of integer points in this fundamental parallelepiped at height I. So in this example I've done, well, we have 1 point at height 0, 1 lattice point at height 1, and 1 lattice point at height 2. And so we get that the H star polynomial is just 1 plus c squared for this simplex. So this is like a result in classical Ehrhart theory. Stapledon generalized this to equivariant Ehrhart theory of simplices. So he basically showed that it works how you would think it might work, where the coefficient of z to the I is going to be the permutation character of the action of the group on the points in the fundamental parallelepiped at height I. So the action of G on the simplex extends to an action on the fundamental parallelepiped, where the extra dimension is just constant, or it's the trivial representation. And so using that, you can come up with this result. So in this case, I took the cyclic group acting on P by rotating cyclic rotation of the vertices. And all of these points in the fundamental parallelepiped are fixed by that action. So at each point, at each height, I just get a copy of the trivial representation. So it's like not a super exciting example, but we wanted to see if we could use this to sort of build up the equivariant Ehrhart theory of some other polytope by looking at these simplices. But the difficult thing is that now, instead of just triangulating the polytope any which way, we need it to the triangulation to agree with the group action on the polytope. And so Sophia and Donghyun and I found that, so basically there's two versions of this theorem, but they're both saying if you have some triangulation that obeys some really sort of specific condition, then you can construct the H star series from that. So I give you one example here. So we say if we have a G-invariant lattice polytope with a G-invariant half-open triangulation where every face of the triangulation is full dimensional and every orbit under the group has order size of G except a unique orbit of size 1, then we get exactly what we want. The H star coefficients are the permutation characters of the action of the group on the points in the fundamental parallelepipeds of all the simplices at height I. And this tells us polynomiality and effectiveness of the H star series. So as an example, here we have the hexagon, the permutahedron. We just take the cyclic group, cyclically shifting the coordinates. And then we can take this half-open triangulation here, which is invariant under the action of the cyclic group. So there's one orbit of size 1, which is this triangle in the middle, and then there's an orbit of size 3, which is size of the group, which is these blue triangles. And so if we look at the points in the fundamental parallelepipeds of all of these half-open simplices at each height 0, 1, and 2, we get these points listed in this table here. And the interesting case happens at height 1, where so we have this point 1, 1, 1 that's fixed by the cyclic action. So that gives us a copy of the trivial representation. And then we have these points 0, 2, 1, 2, 1, 0, and 1, 0, 2 that like cyclically map to each other under the action of the cyclic group on 3 elements. And so this gives us a copy of the regular representation because it sort of models the group acting on itself by multiplication. So that's sort of an example of how this theorem would work in practice. One issue, though, is that it's very difficult to tell if these like triangulations are like widely or widespread, I guess, these like very nice triangulations that agree nicely with the group action. So so that's like another open question about this. And well, yeah, so I'll so just to wrap up, I want to sort of give just like a bullet point list of all the different techniques that have been worked with. So I mentioned zonotopal decompositions. This was done for the permutahedron by myself with Federico and Andrés, and also with Sophia and Donghyun. We did a little bit with graphic zonotopes with the isomorphism or the automorphism group of the graph. For G-invariant triangulations, as I was just talking about, so we have some results with Sophia and Donghyun, and then also I'm aware of some ongoing work by Dali and Delucchi, sort of trying to say this more in the context of commutative algebra. Then another technique that I didn't talk about is having a combinatorial interpretation of the coefficients of the H star polynomial. That sort of lends itself nicely to a group action. So we have a nice example of this with hypersimplices. My co-author Donghyun had this result about like a combinatorial interpretation of the H star coefficients of the hypersimplex. And then we also did some stuff about existence and non-existence of these non-degenerate hypersurfaces, which is that third condition in the conjecture that I didn't mention. And finally, Sophia implemented equivariant Ehrhart theory in SageMath, so you can do computations there. So I'll leave you just with this nice list of further questions. I know I'm a little over time, so I think that's all I want to say. Thank you.
Okay, let's thank Mariel. And so there were a couple questions and discussions going on in the chat. Maybe I'll, for simplicity, start with Alex's question, who said, maybe what is the half-open triangulation? Sorry, what is a half-open triangulation exactly when triangles have an odd number of facets?
Yeah, okay, so let me go back to the example. So we have like a formal definition of this in our paper, but basically it just means that like some of the facets are included and some of them aren't. You're taking like the face lattice of the triangulation and you're decomposing it in a nice way, basically, where yeah, that obeys some specific rules. Yeah.
And then there were other questions, starting with Nicholas's question, is there a nice description for the Ehrhart theory of the dihedral group with a regular n-gon? And I think I'll just skip the other discussion and let you answer that
Okay,
from your
that's a good question.
because I don't know. Yeah.
I think my answer is like off the top of my head, I don't know what it would be, but it also sounds like something that maybe even Stapledon did possibly in his paper. I'm not completely sure. So that's a good question. I'm not prepared to like give you a good answer, but I think there should be for sure. Yeah.
I think there was some, okay, so to maybe summarize the follow-up discussion, there was some concern that regular polygons would not be lattice polygons in general, and so you couldn't even talk about their equivariant Ehrhart theory.
Yeah, so
I don't know.
yeah, I mean,
oh, but then okay,
yeah,
I'm trying to summarize. If other people want to raise their hand and ask the questions, please do so.
Yeah, so to quickly summarize the conversation in the chat, I said the regular n-gon isn't a lattice polygon, which is true in Z2, but then pointed out you could embed it in some appropriate high dimensional space. For example, it's like a slice of your Permutahedron, where you do have also the dihedral subgroup of Sn, like some natural ones working on the Permutahedron. So yeah, it does seem interesting. I mean, it's actually, I guess, an extension of your cyclic group on the Permutahedron. You can just add in a collection, get a dihedral group. So
yeah,
all right. So we all agree that it's an interesting question.
I think it's an interesting question. Yeah.
All right. Any maybe one last question from anybody? Are there any last questions?
Yeah, I had a question. So did you, when you were looking at what happens for the Permutahedron under the action of Sn, did you do anything about trying to see how specific the multiplicities of specific characters behaved? For example, how often the trivial character comes up in the various powers?
Well, that's a really good question. No, only to the extent that Stapledon had some conjectures about the trivial character specifically and like where it appeared in certain places. And so we verified those conjectures for the Permutahedron. But other than that, we didn't, we didn't look at other characters or anything like that. Yeah, we didn't really like analyze these like very ugly, long, non-polynomial. Yeah,
that's why I thought by taking a specific, the behavior for a specific character might be very nice, whereas if you try and look at all of them, it might be a mess.
Yeah, especially maybe the trivial one.
The trivial one or the alternating character would be the other obvious one to try. Or hook characters. So there's various nice characters around.
It looks like in this case, maybe just 2x2 box character is the only one that isn't part of the infinite series.
Yes, but then in some of these lower coefficients, I guess you don't have the other ones. Yeah.
Okay, it looks like we also have a hand raised from Nicholas, and then we'll go to the puzzles. So go ahead.
Oh yeah, no, I was just gonna ask if there are any nice evaluations of the H star polynomial. Like when you evaluate at one, you get something like the natural like thing that you had him like embedded on, right? But like I don't see any. I don't know if there are any other values that give you some information right away.
You mean, sorry, so are you asking about the equivariant series?
Yes. By the H star actually, just like in the equivariant series it should be like that. I didn't think fully about the H star, but I was just asking if there's any values that we should evaluate it at.
Yes. I'm just blanking a bit on like Stapledon's original result, but I think he also had some result about what you get when you plug in z equals 1, for example. And I don't remember exactly what it is. I'm sorry. But yeah. So yeah, refer back to Stapledon's equivariant Ehrhart theory, lots of conjectures, like lots of like interpretations of like, yeah, how like different properties of the polytope might affect the equivariant H star and things like that. But he calls it phi, he doesn't call it H star, but it's the same thing.